we are continuing the discussion of Bijaganita of Bhaskaracharya. So this talk will be continuing with the analysis of the Chakravala process or the Chakravala method. First I will remind you what we discussed yesterday, the basic algorithm of the Chakravala method. Then I will summarize the analysis made by Krishnaswamy Iyengar. Then we will go to the currently known or what is taught in the textbooks for the solution of this equation. The equation x squared minus dy squared is equal to 1 is known as the Pell's equation. How it was solved in Europe in the 17th and 18th centuries. Then I will compare the solution of Bhaskara or the older Chakravala method of India with the Brouncker, Wallis, Euler, Lagrange method of solution. Finally, I will say something about the optimality of the Chakravala method. So, as I said, the Kuttaka condition which was there in the Chakravala method was replaced by the simpler condition that pi plus 1 is divisible by ki by Krishnaswamy Iyengar, and so the algorithm, Chakravala algorithm that we are using will be in this form. To solve x squared minus dy squared is equal to 1. Remember, d is a non-square integer and you want to find out x and y in integers. So you start with initial values, x naught is equal to 1, y naught is equal to 0, k naught is equal to 1, p naught is equal to 0. In any step xi, yi, ki such that xi squared minus dyi squared is equal to ki, find the pi plus 1 such that these two conditions are satisfied. Pi plus 1 is divisible by ki, pi plus 1 squared minus d is minimum. Then once pi plus 1 is found, you can find out yi plus 1, ki plus 1 and xi plus 1, and for that use this auxiliary quantity ai, whose significance we will see in a minute. Ai is defined as pi plus 1 by ki and epsilon 1 is plus 1 if d is greater than pi squared and epsilon I is minus 1 if d is less than pi squared. So this xi plus 1 and yi plus 1 that you have calculated satisfy xi plus 1 squared minus dyi plus 1 squared is ki plus 1. Now the ki plus 1 value could be anything, so you have to keep iterating the algorithm till you get plus 1, in which case the problem is solved. But you can always do bhavana. If you find minus 1 or plus minus 2 or plus minus 4, you can always do bhavana and go to the solution. So this is the Chakravala algorithm that we discussed in the last class. So to recollect, take x squared minus 67y squared is equal to 1. So here the initial step is x is 1, y is 0, p is 0, k is 1. So next step, pi plus 1 is divisible by ki and pi squared is closest to 67, then we have to choose this to be 8. Then 8 squared minus 67 by 1 will be minus 3. So the next step pi and ki will be 8 and minus 3, and if you use the formula I gave you, xi and yi will turn out to be 8 and 1. This of course the trivial thing, 8 squared minus 67 into 1 squared is minus 3. Next step, so 8 you have to add pi plus 1 such that it is divisible by 3. So possibilities are 4, 7 and 10. Of them 7 squared 49 is closest to 67, choose 7. So 7 squared minus 67 divided by minus 3 is 6. So in this case you get p and k to be 7 and 6. You can fill up this ai column also. A naught is 0 plus 8 by 1, that is 8. A1 is 8 plus 7, 15 divided by 3, that is 5. So in the next step from 7 you have to find out pi plus 1. So it should be divisible, the sum should be divisible by 6. 5 and 11 are the possibilities. 5 square is closer to 67 than 11 square, choose 5, then you will get 5 and minus 7. So at this point you have 90 squared minus 67 into 11 squared is minus 7. Next step you go, you will immediately get a k of minus 2. So to 5 you have to add a pi plus 1 such that the sum is divisible by 7. Possibilities are 2, 9 and 16. Amongst them 9 has the square closest to 67. So you put 9, then 9 squared minus 67 divided by minus 7 is minus 2. So you have reached the kshepa of minus 2. You can do bhavana. At this point 221 squared minus 67 into 27 squared is minus 2. You do the Bhavana with 221 and 27, you obtain the final solution 48842 squared minus 67 into 5967 squared is equal to 1. So let us summarize how Krishnaswamy Iyengar analyzed this algorithm. He proved that this process always leads to k is equal to 1. He also showed that the process is different from what is known as the Euler-Lagrange method, which is based upon the simple continued fraction expansion of root d. I will explain all these things. So now first step, let us start with xi squared minus dy squared is equal to ki. Think of an auxiliary equation like this, pi plus 1 squared minus d into 1 squared is pi plus 1 squared minus d. Do the Bhavana of these two, then you will get this product on the right hand side, right. But take this product to the, take this ki to the denominator, then you get an equation like this. If you divide the product of these two by ki squared, then you will get an equation like this. So by doing just the Bhavana of these two equations, you have obtained this. You can recognize these are the quantities appearing in the steps of the Chakravarla equation. So the first thing is to show that the quantities that appear in this algorithm are all well defined and non-negative. So that was the first thing that we have to do when we analyze the algorithm like this. So what can be shown is, it is very simple. If we assume that xi, yi and ki are mutually prime, that means they have no common divisors, and if we choose pi plus 1 such that yi plus 1 is equal to yi pi plus 1 plus xi by mod k is an integer, that was the Kuttaka version of the Chakravarla algorithm, that the first condition was put in the Kuttaka way. This is chosen to be an integer by the algorithm. Then you can show, assuming that xi, yi, ki are prime, then you can show by this algebraic relation that xi plus 1 and ki plus 1 are also both integers. So that is the first thing. And if you write the algorithm for the next step, you will get an equation like this, and that equation can be simplified into this form, which will show you that is ai plus 1 or pi plus 2 plus pi plus 1 by ki plus 1, that is these have to be integers. So Krishnaswamy Iyengar's equivalent version is just obtained by second iteration of the algorithm. Therefore these were the first 2 points in Krishnaswamy Iyengar's proof. He showed first that the algorithm is well defined, that these quantities are all integers if you start with an initial situation. Then he showed that the Kuttaka condition is equivalent to a condition like this. So this algebraic relation shows you that ai is an integer if and only if pi plus 1 by ki plus 1 is an integer, and that is what gives you the equivalence between the two. Then comes the proof that this always converges to k is equal to 1. That is somewhat more complicated. That is based upon what is known as the theory of quadratic forms. I will not tell you in detail. A quadratic form ABC is something like this, ax squared plus 2bxy plus cy squared. Krishnaswamy Iyengar is using this ki's, pi plus 1 and ki plus 1 to make a quadratic form, and that pi plus 1 squared minus ki plus 1 is equal to d. Two quadratic forms are equivalent if b squared minus ac is the same for both of them. So you have a class of all quadratic forms of the form ki pi plus 1 ki plus 1 such that they have this discriminant d. Then he defined a quadratic form to be a Bhaskara form when this kind of a condition is satisfied. And now in the Chakravarla what is happening? You start with a k naught and a p naught, then you go to p1 first, from that you will find k1 also. So in the Chakravarla you will successively get successive quadratic forms. So the successor of a Bhaskara form by doing Chakravarla process, Krishnaswamy Iyengar showed, is also a Bhaskara form. And then he even showed that you can start with any value of k and do Chakravarla, you will eventually come to a value of k which is less than root d, and later on you will move within the region k less than root d and p less than 2 root d. So both k's and p's are bounded by root d and 2 root d, and k and p are integers, and if they are bounded by root d and 2 root d, after some time they have to repeat in a cycle. So, already the cyclic property of the algorithm is proved. Finally, he showed that amongst the set of all equivalent cycles of by doing the Chakravala process, the Bhaskara forms go in a cycle. He showed that any two cycles of Bhaskara form are not equivalent, and all equivalent Bhaskara forms come in the same cycle. To do that proof, he used the older proofs that were done by Gauss for quadratic forms, for what was known as the Gauss forms, and therefore he was able to show that you start with any k whatsoever, you start with any xi, any yi such that any k is there, xi squared minus dyi squared is equal to ki. Go on doing Chakravala, you will always first come to a value of k less than root d, and eventually you come to the value 1, and so this was the proof of Krishnaswamy Iyengar. Now we quickly go to the Euler-Lagrange method. So what is the history of this? So in 1657, Fermat, the famous French mathematician, he posed a challenge to the British mathematicians. First he wrote to his friend Frenicle de Bessy saying that, can you solve these two equations, 61x squared plus 1 is equal to y squared and 109x squared plus 1 is equal to y squared for x and y in integers. Already you see that the 61x squared is coming there, and within a couple of months he wrote this as a problem and sent it as a challenge to mathematicians in France, Belgium and England. The question was the same thing, can you solve the equation x squared minus dy squared is equal to 1 in integers? And he said, people know this kind of an equation, but the important thing is to put the restriction that you want solution in integers, and this is the birth of the theory of numbers in modern mathematics, as Andre Weil says that this was the birth of theory of numbers, essentially the problem. Now it was sent to England. William Brouncker was the president of Royal Society, and his friend John Wallis, who was the professor in Cambridge prior to Newton. So both of them wrote down the solution. First they wrote down the rational solution that Brahmagupta had written down in 628 and sent it to Fermat. Fermat said, you are cheating, I had asked you for integral solution, rational solution is trivial. So then of course they sat down and worked out the integral solutions. Fermat had asked for 4 particular cases. To Frenicle de Bessy had asked for d is equal to 61, d is equal to 109. So he had posed the problem for 149, 109 and 433. He knew that they are going to involve large number of steps. So to check that you are proficient in Chakravala, you solve the Chakravala for all these the Varga Prakriti equation for all these 5 examples. 61, 4 examples, right? D is equal to 61, 109, 439 is it? What was it? 433 and what's the other one? 149 and 433. If you do that, so just this visa already gives you solutions which go to trillions, the order of magnitude of x. So the solution was communicated by Brouncker and Wallis in letters, and then Wallis published all this in 1657 in Latin, and later on he wrote a famous book on algebra in 1685 where this solution was put in. That algebra equation came in Latin. It is one of the earliest science books in English, Wallis algebra, written in 1685. Now Fermat of course wrote to the English mathematician saying that he willingly and joyfully acknowledges the validity of their solutions, but privately he complained to his friend Huygens that they had cheated, they had not given him a general proof that they were asking, and he said this proof must be based upon the method of descent. Fermat proved very little in his long career, but he suggested a lot of theorems for which he wrote in the footnote saying I have a proof which is too long to be communicated here, and many of them were based upon the method of descent. Now Euler in 1730 starts again this his journey into the same equation. It is like Kuttaka, starting from larger numbers coming down to smaller numbers. Kuttaka is the standard method of descent. Euler in 1730 describes Wallis method and ascribes it to John Pell, and so naming of this equation as Pell's equation is due to Euler. Euler wrote a famous book on algebra and where he called it Pell's equation. and that name has stuck. And he shows that first Euler starts showing that there are infinite number of solutions. Then in 1759 he gives a method for solving based upon the simple continued fraction expansion of root d, and he also gives a table of solutions from 2 to 120 for this. And in 1764 Euler rediscovered the Bhavana principle. He called it the most elegant theorem, elegantissimum, meaning taratama as we say in Sanskrit. So this is the most elegant theorem. And in 1768 to 70 Lagrange wrote a series of papers where he proved everything that Euler had done. So the Euler method became well established and proved by 1770. So what is the method? So what is a simple continued fraction? So normally a0 plus 1 by a1 plus 1 by a2 plus 1 by etc., further division like that is called a continued fraction. It is called a simple continued fraction if only ones appear here. a0, a1, a2 are all integers, they are positive after the first one, the first integer can be negative. So there are various ways of denoting, because this way of writing it will take too much space. So one way of denoting it is by writing it this way, another way of denoting it is by putting that plus in the denominator. It's typographically inconvenient in typewriters, but while writing it's quite easy. Now how to get a continued fraction associated with any real number? Just pay some attention to this. The first partial quotient, these are called partial quotients. The first partial quotient a0 is just the integral part of alpha. What is the integral part of alpha? If the number is 1.3, integral part of that is 1. If the number is 1.9999, the integral part of that is still 1. Now subtract integral part of alpha from alpha, so that will lie between 0 and 1. Take 1 over that, take the reciprocal of that, that will be much more than 1, that is called that alpha 1. Take the integral part of alpha 1, call it a1. And now alpha 1 minus the integral part of alpha 1, take the reciprocal of it, this is again a number larger than 1, take the integral part of that alpha 2, that is a2. So that way you start getting your a0, a1, a2 etc. a0, a1, a2 are called partial quotients, alpha 1, alpha 2 are called complete quotients. So let us try this example. 149 by 17, we want to express this as continued fraction. So basically this is 8 plus 1 over no 120 no 9 8 only 80 plus 136, so 13 by 17, right? So now write invert this, so this 1 over you are seeing some similarity with what we were doing earlier. So this will be 8 plus 1 over 1, is it? 13 plus 1 plus 1 over 3 plus 1 over 1, something like this. 8 1 3 4, I am saying getting where is the 4? Oh yes. So this how it will look. By mutual division you can get the continued fraction for any rational number, and if it is a rational number the continued fraction terminates, and if it is an irrational number it does not terminate. Here are two irrational numbers which have a nice continued fraction, 1 plus root 5 by 2 called the golden ratio. Its continued fraction is 1 1 1 1 1 1. E, the base of natural logarithms, has a nice continued fraction 2 1 2 1 1 4 1 1 6 1 1 8 1 1 etc. Unfortunately pi does not have a nice continued fraction. Calculating the 10,000th partial quotient of the continued fraction of pi is as difficult as calculating the 10,000 decimal place of pi. So they are equally random. Now this, you have a continued fraction like this, you stop it at any point, then that will become a rational number, you calculate it, it can be written as Aj by Bj, that is called a convergent of the continued fraction. So these convergents satisfy recurrence relations. These are essentially what is there in the Valli process of Aryabhatta. This calculating the convergent backwards is the Valli, these recurrence relations are the essentially the Valli relations. This A0, A1, A2 are the quotients that come in the mutual divisions of the Bhajya and Bhajaka in Kutaka. And these convergents have to satisfy this property Aj Bj minus 1, Aj minus 1 Bj is minus 1 to the power j plus 1. So Aj Bj are obtained if you have a continued fraction, whether it is terminating or not terminating, you terminate at any point, you get the corresponding convergence. So those will be rational approximations to the irrational number that you have. They will be optimal in some sense. So the convergence of this are, so you can straight away see, if you terminate it here, it is 8, then 8 plus 1 over 1. So 8 by 1 is the first convergent, 9 by 1 is the next convergent if you terminate it here. If you terminate it in the place 3, you will have 35 by 4, and if you go all the way, it is 149 by 47, 17, sorry, whatever we started, thank you. So these are approximations to 149 by 17, they are in some sense best approximations. A later Kerala book called Karna Paddhati gives very nice algorithms for doing these convergence and uses them as approximations, because the number of civil days in a Mahayuga is in trillions, the number of solar years in a Mahayuga is also in 43,20,000 years in 2000, and you need ratios of these to calculate the positions of sun. So those numbers, fractions are very huge, and you can always approximate them by fractions with smaller denominators, and the best approximations are what are provided by the continued fraction expansion of it, and Karna Paddhati excels in giving this, making use of this continued fraction kind of results.
Is it 9 by 2 or 9 by 1?
Yes sir?
9 by 2 or 9 by 1?
Oh, 9 by 1 sir. 8 plus 1 by 1, 1 plus 8 plus 1 by 1. What I have written in the slide is always more accurate than what I do on the board, which is done at the spur of the moment. Another interesting thing, just the connection with Kutaka, this previous convergent, we wrote this relation Aj Bj minus 1 minus Aj minus 1 Bj is minus 1 to the power j minus 1. So you have the relation, you use this convergent 35 by 4, 149 into 4 minus 35 into 17 is equal to 1. So for this 149 by 17 and 35 by 4, this will be the two solutions for the Kutaka equation involving 149 and 17. So the entire continued fraction theory is as old as Aryabhatta's Aryabhatiya, basically the entire thing is there. Now coming to our problem, solution of the Varga Prakriti, Euler showed that square root of d can always be written as a periodic continued fraction. Periodic means at the end of this, whatever I put in the bar will keep repeating itself. In fact, we saw one nice quadratic surd which had a periodic continued fraction expansion. The period started right at the beginning, right? This is equal to 1 comma 1 comma, so it is nothing but 1 bar. It is a period, starts at the right at the beginning. So all quadratic surds have a periodic continued fraction and vice versa, and root d is always of this form with the last entry 2a0, if this is entry is a0. This is called a period. The period can be odd, period can be even, and the penultimate convergent here at the end of the period will give you the solution for minus 1 if the period is odd, it will give the solution for plus 1 if the period is even. If you obtain the solution for minus 1, you do bhavana and get the solution for plus 1. So if the period is odd, then you will get the solution for x squared minus dy squared is equal to minus 1 at the end of the period. So let us take this example, x squared minus 13y squared is equal to, this is the given example given in Euler's book. Square root of 3 is 3 plus 1 over 1 plus 1 over 1 plus 1 over 1 plus 1 over 1 plus 1 over 6. This bar means now again the same thing will start here. It will go on repeating itself. It is an irrational number, so continued fraction is infinite, but it is periodic. You have to take this convergent at this point, 3 plus 1 by 1 plus 1 by 1 plus 1 by 1 plus 1 by 1, stop it here. Then you will have A4 by B4, which is you can see to be 18 by 5. In fact, we saw this solution yesterday while discussing the equation x squared minus 13 y squared is equal to minus 1. The solution by Bhaskara was also this 18 and 5. Now doing bhavana of this with itself, you will obtain the solution for k is equal to 1. So this is Euler method, or we can call it Euler-Lagrange method. Lagrange wrote down all the proofs. Now from these simple continued fractions, you should go to something called semi-regular ones. How are they different? Instead of only plus 1s occurring here, plus 1 and minus 1 can both occur here. That is called a semi-regular continued fraction, and certain mathematical conditions which we can ignore, something like this should be satisfied. So the convergence of the semi-regular continued fraction will involve these epsilons in their recurrence relations. We saw this recurrence relation in Chakravala then itself. So first thing that Krishnaswamy Iyengar did was to show that the Bhaskara method or the Chakravala method, at the time of Krishnaswamy Iyengar, he was not aware that there were people prior to Bhaskara who had done the Chakravala method. He of course mentions that Bhaskara is saying only that Chakravala midam jaguhu, so this must be some method which was earlier known to Indians. So he showed that the Chakravala method corresponds to expanding root d as a semi-regular continued fraction. A0, A1, A2 are all given by our quantities, familiar pi plus 1 by mod ki. This epsilon I was also defined there. So you go back to that table, you can immediately write down there. So root 67, the Bhaskara's continued fraction. A0 is 8 plus 1 over 5 plus 1 over 2 plus 1 over 1 plus which column I am writing, 8, 5, 2, 1, 1, 7, okay. It goes up to 16, okay, that is fine. So 8 plus 1 over 5 plus 1 over 2 plus 1 over 1 plus 1 over 1. Oh, I am writing down the Euler-Lagrange, so I okay. This is, let go back to Chakravala. This mouse is refusing to cooperate with me. Okay, we will give it the due time. So 8 plus 1 over 5 plus 1 over 2 plus 1 over 2 plus minus 1 over 9 minus 1 over 2 plus, I will continue writing it here, one by 2, 1 by 5, 1 by 60. So this is the semi-regular continued fraction expansion. Notice that there are 2 minus 1s appearing here. And of course, the whole thing is periodic. That will keep repeating itself, 5, 2, 2, 9, 2, 2, 5, 16. Forward movement is fine. So first thing Krishnaswamy Iyengar showed was that the Chakravala method, you can immediately write down the square root of d as a continued fraction. Next thing he pointed out that the simple continued fraction algorithm can be viewed as a similar to Chakravala algorithm, only you change the condition of Bhaskara, that modulus of p plus 1 squared minus d being minimum, you change it to the condition that d should be greater than pi plus 1 squared and d minus pi plus 1 squared should be minimum. So the value of pi plus 1 should be so chosen that it is less than, its square is less than d and it is closest to the value of d. And if you change it to another condition, pi plus 1 minus root d is minimum, you obtain what is called the nearest integer continued fraction. We will see it later in the context of Narayana, maybe if we have time. So now I am doing the Chakravala algorithm to reproduce the Euler-Lagrange method. So where is it differing? To see where it is differing these two places, these two rows which are highlighted, those two rows are skipped in Chakravala. So how do we see that? So you remember this, in the step 3 you have 5 minus 7 and the solution is 90 11, right? And now what does Chakravala give us? 5 minus 7 90 11. Now to 5 you could have added 2 or 9 or 16, but in the Euler-Lagrange process 9 is barred. 9 squared is 67, that is larger than 9 squared is 81, that is larger than 67. So you have to choose only 2 which is lesser than, whose square is lesser than 67. So amongst the allowed values, so here we have to put pi plus 1 to be 2, and here also 9 is appearing in this step. So these are two steps here in Chakravala which are not allowed in the Euler-Lagrange. In both these cases epsilon is minus 1, whenever p squared is greater than d, epsilon will be minus 1. That is the sign that a step in Euler-Lagrange is being skipped by Chakravala at that point. So the minus 1s are hallmarks of the Chakravala process. So if we remember there, what was the next step in Chakravala? Next step is 221 and the step after that is 1899. Remember these two, we are going to see the Euler-Lagrange process here. So 90, it comes to 131, then goes to 221, then goes to 1678, then goes to 1899. So 2 extra convergents are added, 2 extra steps are added in the Euler-Lagrange process. After all, historically it did come 500 years or 600 years after the Chakravala process, so it has to have that much more weightage in it. So the square root of 67 can be expressed as a simple continued fraction. It will look like this. Written as a semi-regular continued fraction, it will look like this. So the period here is 1 2 3 4 5 6 7 8 9 10. The period here is 1 2 3 4 5 6 7 8. So 2 steps are eliminated in 67. So we can look at the great the old friend 61. So in the Euler-Lagrange process it will take 22 steps. Chakravala would have taken 14 steps. But actually you do not need to do all the 22 steps. The simple continued fraction will terminate here when you get minus 1, k is equal to minus 1. So it is a square root of d which has a odd period. So Chakravala is indeed a hot subject. So so it has an odd period, you are getting this minus 1, it will take 11 steps, and to get that 11 steps 1 2 3 4 extra steps Euler-Lagrange adds. Chakravala will come in 7 steps instead of 11. So this we can see by looking at the two continued fractions. The simple continued fraction has 1 2 3 4 5 6 7 8 9 10 11 entries for 61. It has 1 2 3 4 5 6 7 entries in the Chakravala. So the period has 7, that is this has 7 steps, this has 11 steps, and these precise 4 minus 1s are appearing. Those are precisely the points where the pi is crossing root d, pi squared is crossing root d. Okay. So we have said enough about the comparison of the two. We will say something in the end. So Krishnaswamy Iyengar then does various things that people normally do with continued fractions. he first showed that the Euler-Lagrange formalism can be viewed as a modification of the Chakrawala, and he also showed that Chakrawala can be viewed as a generalization of the continued fraction. Instead of using a simple continued fraction, you use a semi-regular continued fraction where +1 and -1 are both allowed. Now to give a direct algorithm for he called these continued fractions that come in Chakrawala as Bhaskara continued fractions. Nowadays they are called the nearest square continued fractions. So they can be called Bhaskara or the nearest square continued fractions, and he gave a general rule that whenever you have a quadratic surd, I explained to you the simple continued fraction algorithm. Take the integral part, subtract the integral part from the number, take the reciprocal part, again take the integral part, subtract that from the number, so like that go on. That is the simple continued fraction algorithm. So for the Bhaskara continued fraction, he gave an algorithm not for a general real number, he gave the algorithm for a quadratic surd, because that is where the Chakrawala process is appearing. It is appearing in the context of a root d. So if you write root d as a Bhaskara continued fraction, the total coefficients will come out to be quadratic surds like this. Now see, with a particular property that p and q and d minus p squared by q are integers which are prime to each other, that is called the standard form of the surd. So at any step doing the Bhaskara process and doing the simple continued fraction process, how do they differ? So to show that, you take this quadratic surd, write it this way, where a is the integral part of p plus root d by q, and you take this quadratic surd, you write it as, just write it as a plus 1, whatever remains you write it in the quadratic surd form, that is how it will look. And so Krishnaswamy Iyengar said, if p prime squared minus d is less than p double prime squared minus d, or when they are equal, if q is less than 0, choose a and set epsilon is equal to 1. In the other case, choose a plus 1 and set epsilon is equal to -1, and then he showed the relation between the quantities which appear in the Chakrawala algorithm and the quantities this k and the q which appear in this continued fraction expansion. So you choose a when p prime squared minus d is less than p double prime squared minus d, that is all that. Okay. Next he also studied the periodicity properties of the continued fraction. Now just look at this, let us look at the case of 61. You see there is a complete periodicity here, a1 to ah minus 1, ah minus 1 to a1 and a 2a naught, a1 to ah minus 1, ah minus 1 to an and a 2a naught. So similar periodicity exists for the Bhaskara continued fraction also for most of the situations which Krishnaswamy Iyengar called as type 1, where certain condition does not happen, certain kind of complete quotients do not occur. The Bhaskara continued fractions have the same symmetry, but in some particular cases they have a more complex symmetry, and these are examples where the symmetry is more complex. 29, 53, 58, 97, the Bhaskara continued fraction does not have the kind of symmetry that the simple continued fraction has, it has a more complex symmetry. Similarly, one can identify when you are doing the continued fraction expansion when the midpoint occurs. Euler had identified that. So similar midpoint criterion have been found out in recent times. Krishnaswamy Iyengar did not write it in his time. In the last 5-6 years there are many others who are working on this kind of problem. They have identified the midpoint. In fact, this entire subject of x squared minus d by 1 squared is an equation which is of great interest even contemporarily. One is, it's a very it's one of those algorithms which are non-polynomial time, that is the amount of time that is taken to solve this in general is of the order of d times e to the power square root of d. So it is a non-polynomial kind of an algorithm. So there is even now a quantum algorithm by Hallgren which will solve this in a polynomial time. Of course that can be implemented only in a quantum computer which may come in the next 200 to 300 years. Then there are also many other interesting properties of this equation. Several books are written. Few of them do mention that Brahmagupta and Bhaskara did solve, and some people say partially, fully. Some books do explain in a fairly nice way the way the equation was solved by Chakravala. But the most important thing for us is that the old method was indeed the best method. The Chakravala method, as I said, showed you, does skip various steps. So in that sense it is optimal. Whenever you have an algorithm, one of the important thing you want to see is whether you are doing it in the minimal amount of number of steps. And it happens in many cases that the period of the Euler-Lagrange continued fraction can even be double or almost double the period of the Bhaskara. I have given 5 cases. Here is a case where the period is 3 there, period is 5 in the case of Euler-Lagrange. For Bhaskara the period is 3. For 44 the Bhaskara period is 4, the Euler-Lagrange or the simple continued fraction the period is 8. It is indeed double the number of steps. And if you see wherever this is happening, the number of negative signs are a indicator of the number of steps which are being skipped. I am seeing your plight, but I have to complete this. Yes, sir.
Does it mean that the initial feasible point at which the Bhaskara's thing starts is closer?
No, they both start from 1 0.
No, not that way. When they take the first integer a.
No, even that is not so. The algorithm is more optimal. It is allowing both pi plus 1 larger than square root of d
Yes.
and pi plus 1
That is what
lesser
I mean,
than.
yeah.
So allowing both the possibilities.
That
So
seems
it
to-
makes you go closer in a more nicer way.
Fine.
In fact,
Okay.
even this Kuttaka, even this, you see in each of this step, what I was doing is I was taking the remainder. Instead of it, I can take the nearest integer. Then the number of steps needed in reducing even a rational number into a continued fraction will be less. It will be less than the number of steps needed when you are always taking the lower the divisor to the remainder to be positive. The remainder can be taken to be both positive and negative to reduce the number of steps. So that is what is being systematic, but it cannot be done arbitrarily. What Brownker and Wallace did was they tried to do plus and minus arbitrarily. Bhaskara or Jayadeva or whosoever discovered Chakravala prior to him had a systematic algorithm for doing this. Now there is another interesting property discussed by a famous Swedish mathematician Selenius, that the issue is this: whenever there is a sequence of what are called the unit quotients, we will go to the previous step, then you will see the moment I am able to reach. Okay, take the simple continued fraction. You see there is a set of 1 1 1 1 appearing here, right? Whenever these are these partial quotients, whenever such ones appear, the Chakravala gets rid of them. So these are called uni-sequences. Here there is a uni-sequence of length 4. Here also there is a uni-sequence of length 3 followed by uni-sequence of length 3. Here there is a uni-sequence of length 6. So whenever there is a uni-sequence of partial quotients, so whenever this A0, A1, A2 that you are seeing, when they become 1, Chakravala kills them, that step. So okay, so whenever you have a uni-sequence of partial quotients of length n, the Chakravala process skips exactly n by 2 steps if n is even, and n plus 1 by 2 steps if n is odd. So that is at the heart of the Chakravala process. And Selenius, who sort of studied these uni-sequences in great detail, the Swedish mathematician I was telling you, he showed that the remaining convergents are actually the optimal convergents, in the sense that bi modulus ai minus bi root d, they are minimal. So of the n plus 1 convergents possible, Chakravala picks out the closest convergents and throws away the ones which are not that close. Of course, even simple continued fractions, all convergents are fairly close, but Chakravala picks up the ideal ones or the most optimal ones amongst them, and that is what Selenius showed, and he generalized the theory to what are called optimal continued fractions for arbitrary real numbers. So recently Matthews and there is a group in Australia who are working on Chakravala systematically. They were the people who showed the midpoint criteria and things like that. So they have tried to estimate by computer simulation, take the ratio of number of steps taken by Euler-Lagrange and number of steps taken by the Chakravala algorithm, divide one by the other, and the ratio is converging to something like log of 1 plus root 5 by 2 or 0.694 etc. So something like 30% saving is what could be achieved. There is a great mathematician called D.N. Lehmer. About 60-70 years ago he was known as one of the pioneers in computational number theory. So he wrote in Mathematical Reviews in 1940s, early 41 or 42, a review of the paper of Professor Krishnaswamy Iyengar. Incidentally, Professor Krishnaswamy Iyengar is the father of a more well known figure, A.K. Ramanujan, the English professor, former professor of English in Chicago. So he wrote that not only does it destroy the symmetry that the simple continued fraction have, and the few steps that it seems to gain are not really worth the amount of destruction of the beautiful theory of the simple continued fractions that we have arrived with. In fact, more or less a similar comment is made by the great mathematician Andre Weil in his book on history of number theory. Andre Weil even says that this name Pell's equation is very convenient because it is very definitive. I do not know what it means, and so we have to continue using it while referring to this beautiful equation. Anyway, so this is the kind of estimate, numerical estimate, perhaps some theoretical estimates can also be made for the optimality. So these are Krishnaswamy Iyengar's papers. The last one appeared in the Journal of Mysore University in 1941. This is Andre Weil's monograph on history of number theory. This is the famous paper of Selenius. He has written 3-4 papers in German and I think Swedish also earlier. This is the paper of Matthews, Robertson and White, and this group has several papers on nearest square continued fraction. And Jacobson and Williams, they are experts in the study of Pell's equation. This is a book which runs to about 700 pages in the discussion of Pell's equation. So it is a very interesting subject. I have tried to present you what is the mathematical sort of heart of the Chakravala process, which goes back to Jayadeva and Bhaskara. Narayana also has something to say on it, which I will briefly try to tell you during the talk on Narayana. Thank you. If you have some brief questions, we will have quickly. We have 2 minutes.
Sir, how do you think that the Chakravala, achieved optimality directly without going around? So what's your feeling about it?
No, not that way. I think from the time of Brahmagupta, they were worried about solving this equation, and they were not worried about any other theoretical principle, but trying to find out the best way of solving the equation. I mean, you may discover other important mathematics as a byproduct. It is not a byproduct of some other mathematics that you do. And so first Bhavana principle, and then of course this nearest square kind of a method, and they were not aware of the other theories, therefore they could get at a method. This became known to the West. I mean, there are speculations that Fermat knew about Bhaskara's solution because he is talking about the same example, x squared minus 61 y squared is equal to 1, but that link one does not know. But the first time that the modern European scholars came to know was when Colebrook translated Bhaskara's Bijaganita in 1817. After that, many European scholars did look into Chakravala. Hankel, one of the great mathematicians of 19th century and major historians, in fact praised it. He said that prior to Lagrange there was nothing in the history of number theory that was achieved which is similar to this and all that. But after that, I think the only systematic major investigation which took Chakravala seriously as a alternative to the standard, because there are many books just write that this is same as the Euler-Lagrange method, this is same as the continued fraction expansion. So it took the heart of a great mathematician like Krishnaswamy Iyengar with his, he was very clear that Bhaskara was doing something unique and nice and beautiful, and he went into the heart of it and spent about a decade of his active mathematical life in analyzing it, and it's to him that we owe all this beautiful analysis of the Chakravala process of Bhaskara. Thank you.